Hi, so I'm Tousif Islam. I'm a first-year PhD student at the University of Massachusetts. In this talk, I will briefly explain what are the acceleration relations in the galaxies and how these acceleration relations in the Milky Way can be used as a differentiator between different theories of modified gravity. This work has been published here. We have the archive link and the physical review, the URL, in case anyone is interested. Okay, so I'll first outline what are the phenomenological acceleration relations that people have found in different galaxies. The first one we call the Mass-Discrepancy Acceleration Relation. So in Newtonian gravity, which is the Weyl limit of general relativity, the discrepancy between the mass estimated from the observed dynamics of galaxies and the observed baryonic mass, m baryon, so they are found to be correlated with the observed acceleration in the galaxy, showing a monotonous decline with increasing radial distances. Now, the observed relation between the ratio of m observed divided by m baryon and the observed acceleration is known as the mass discrepancy acceleration relation, in short, the MDAR. Recently, in 2016, in this paper by McGaw et al., when they analyzed the data of another 150-ish spiral galaxies from Spark's catalog, they found a more constrained relation between the observed centripetal acceleration and the expected Newtonian acceleration from the observed baryon in galaxies. And this particular relation, they call it the radial acceleration relation. This is something which has been observed for more than hundreds of galaxies, as I have already mentioned. And they provide a phenomenological scaling between the observed acceleration, which we call MLS, as the where MLS are the author's name, and the expected baryonic acceleration. Now, the radial acceleration relation is a very interesting relation because it holds for even other type of galaxies, for example, ellipticals, lenticulars, and dwarf galaxies. The universality of this particular relation provides a unique test for dark matter models and the modified gravity theories at galactic scales. Now, even though these semi-analytical dark matter models can account for RAR, the intrinsic scatter produced by these models is always significantly larger than the one observed. Furthermore, in the context of lambda-CDM, where the dark matter dominates the baryonic mass, it is not immediately very clear that why the acceleration, the observed acceleration, should be strongly correlated with the baryonic matter. In other sense, this might say that that the dark matter is strongly correlated with the luminous matter, which has not been proved yet. On the other hand, it has been found that the modified gravity theories, for example, the modified Newtonian dynamics, MOND, conformal gravity, then scalar tensor vector theory, they have been very successful in explaining the RAR more easily. The next relation we call the halo acceleration relation. This halo acceleration is a new kind of acceleration which has been proposed in the P&O paper in 2019, where the halo acceleration is defined as the difference between the observed acceleration and the expected baryonic acceleration in Newtonian gravity. So in other sense, one can kind of think it as a acceleration that's coming from masses which cannot be seen, or some other effect which we do not know. Now, the relation between this halo acceleration is radial distances and the observed acceleration is called the halo acceleration relation. So in this particular talk, I will explain how these three relations can be explained in two different versions of modified gravity theory, namely the conformal gravity and the MOND, as well as in Newtonian dynamics, and how a Milky Way can act as as a testing ground for these kind of experiments. So one important thing to understand here is that the acceleration range for galaxies that run from 10 to the power minus 12 to 10 to the power minus 8 meter per second square regime, but the low acceleration regime is basically 10 to the power minus 12 to 10 to the power minus 10, and the high acceleration regime is 10 to the power minus 10 to 10 to the power minus 8. Now, where even though RAR has been fit individually to hundreds of galaxies, most of the galaxies either fall in the low acceleration regime or in the high acceleration regime. On the other hand, for Milky Way, we have data for extending far from the galaxy center, meaning that we can cover both the high acceleration and the low acceleration regime. And in that sense, Milky Way acceleration data is very unique in when compared with other galaxy data. Okay, so now the two particular theory we consider here is the first one is Weyl conformal gravity, and the second one is the modified Newtonian dynamics, in other words, which is popularly known as MOND. Now, in conformal gravity, apart from the invariance, coordinate invariance, it also employs the principle of local conformal invariance of the space-time, in which the action remains invariant under the conformal transformation of the metric G nu mu, which has been proposed in Mannheim 1999 paper. Now, if one looks into the conformal gravity, I'll not provide a very detailed analysis of that, but rather we just give an outline of what happens there. Is that one can find that apart from the normal Newtonian potential, one would find a linearly increasing linear potential and a quadratic potential, a negative quadratic potential, in fact. Now, one can show that in conformal gravity, the mass inside the spherical shell as well as the outside mass both contribute to the gravitational potential, meaning that the galaxy dynamics would not only be affected by the masses within the galaxy, but also the masses in the universal masses of the universe. Now, this can be seen in this particular equation that I show in 3.4, that taken from the paper here, is that we'll have the dynamics would be affected by the local mass, which we call the v square local. But then also you have two different terms coming from the universal mass distribution. And then the gamma naught, kappa, and these are the parameter in Weyl gravity, which has been taken from the fits in galaxy and galaxy cluster data. However, the main takeaway from here is that in conformal gravity, apart from the local mass contribution, we also have contribution coming from the masses in the cosmological. For the MOND, however, as we know that it's a phenomenological model, and it modifies the acceleration law in GR in a phenomenological manner. And once you consider all of these interpolating functions in MOND, the final MOND acceleration turns out to be a function of the Newtonian acceleration AN and the and some constant A naught. So we will use these expressions in while computing the acceleration for these particular theories. Okay, so up next here, I described what are the kinematics data we are talking about in Milky Way. For the Milky Way, we have compiled three different studies, one by Bhattacharya et al. 2014, Sofiu 2012, and Huang et al. 2016. We show the acceleration data as a function of the radial distances from the galactic center here in this particular plot in different colors for different studies. And then in the dashed line, we show the 10 to the power minus 10 meter per second square acceleration, which basically differentiates the high acceleration and the low acceleration regime. And as you can see here that the Milky Way data covers both the acceleration regimes, and would thus be very interesting to check the acceleration relation in the light of modified gravity theory. Okay, so now here we model the Milky Way, we provide the mass model that we used in this particular work here. So Milky Way Milky Way consists of a central spherical bulge, and then we have 4 different disks. So we have one thin stellar disk, then we have one thick stellar disk, then we have H1 and H2 gas disk. So the disks have a exponential function mass distribution, and then bulge also have an exponential distribution in the surface density, which then corresponds to a 3-dimensional mass distribution here, as shown in this Valenti et al. 2016 paper, and where this k is basically a modified Bessel function. So once we use this particular mass model and couple it together with our choice of modified gravity theories, we can compute the acceleration for the whole acceleration profile for the galaxy and compare against the data that we have shown here. Okay, so the first acceleration relation we consider is the radial acceleration relation, and here in the upper left we show the inferred mass discrepancy. The observed acceleration, observed centripetal acceleration from different studies, BCK14, YS12, and YH16, as described before, as a function of the radial distances. And on top of that, we provide the expected acceleration profile in Weyl gravity in RAID in the MLS scaling law proposed by McGaw et al. In green, and then in blue we show the expected profile in GR without dark matter, and the MOND profile has been shown in the black. Now what one can see here is that as the radial distances that increases from the center, the GR profile deviates from the observed acceleration, meaning that it's not possible to explain the behavior without adding dark matter. Whereas without the dark matter, Weyl gravity, MLS scaling, and MOND seem to account for the data pretty well. Now in the upper right, we show the observed centripetal acceleration, but now as a function of the expected baryonic acceleration in Newtonian gravity. So which one can see here that it becomes more evident that as the expected baryonic acceleration becomes smaller and smaller, which corresponds to going farther away from the galactic center, the GR deviates from the data, whereas the other models, they agrees with the data well. So apart from the normal data or acceleration data points, we also show in pink the mean averaged acceleration data, and one can see that only at the furthest point, that is for the smaller end of expected baryonic acceleration, the MOND and the MLS scaling that differs from the data a little bit. Then in the lower panel, we show the residuals as a function of radial distances and as a function of the Newtonian acceleration from baryons. The residuals have been squared here, and it's a relative residual. So this makes sure that the data is always positive, meaning you can plot it in the log scale, and also this relative residual, meaning that any difference, any high difference in the initial part of the data where the acceleration is a bit high, that do not contribute unproportionately to the error estimation. Okay, so now here we show the reduced chi-square values as goodness of fits for different theories of gravity and R scaling law. No dark matter is assumed here. As you can see that it is the Weyl gravity, it is the MOND Weyl gravity and radial acceleration relation which does far better than the general relativity without dark matter. And then here we show the histograms for all the theories we have considered here. So this is the histogram of the log residual, and which you can see that the residual histogram for GR without dark matter that peaks at a larger value, whereas MOND and Weyl gravity peaks they kind of overlap. The later two histograms also exhibit longer tails in the lower end of the residual values, and then RAR scaling that produces residual slightly larger than MOND and Weyl gravity. Now with this, we go to the next acceleration relation, which is the mass discrepancy acceleration relation. Now for this particular case here, we compute the dynamic mass directly from the observed acceleration. Similarly, one can also compute the baryonic also get the baryonic mass in terms of the Newtonian acceleration, and then the ratio between these two basically turns out to be a ratio of the observed acceleration and the expected baryonic acceleration in Newtonian gravity. So once we have that, in the upper left here, we plot the inferred ratio inferred ratio as a function of the radial distance in the semilog plot, semilog Y plot. Now we observe that the amount of missing mass, or the ratio of the observed and expected Newtonian acceleration due to baryons, that increases as the distance from the center increases. We find that at larger distances, the MOND and the RAR exhibit similar features, whereas Weyl gravity deviates from these two different theory, and has been able to account for the data better than the other two models considered. Now these features become more prominent when in the upper right, where we plot the mass discrepancy as a function of the expected baryonic acceleration in Newtonian gravity. So which one can see here is that the Weyl gravity is better in explaining the data than the other two models here. Basically, you can what you can see is that in the higher acceleration regime, which is the inferior part of the galaxy, all these theories of gravity, they agree with each other to some extent, but the disagreement grows as the acceleration becomes smaller and smaller. Well, here we then show the residual histogram of the log of residual, and we reach similar conclusion that the MOND and the Weyl gravity, they produces peaks which are smaller than the peaks in the RAR scaling, which is MLS, and the GR scaling. Finally, we come to the halo acceleration relation. We have already said the halo acceleration is defined as the difference between the observed acceleration and the expected baryonic acceleration in Newtonian gravity. As always, we have plotted the halo acceleration as a function of the radius here in the upper left, and we have the Weyl gravity data in red, MLS in green, GR in blue, which would always be 0 here, because in GR the observed and the acceleration and the expected should be same. Then we have the Weyl gravity in red and gravity in red. So what we can find here is that as the acceleration increases, in the middle part from 40 to 80 hertz, basically all of these different theories of gravity, they agree with each other. But as we go beyond 80 kiloparsec from the galactic center, Weyl gravity differs from the other data, differs from the MLS and MOND, and kind of keeps declining when the MOND and the MLS become a bit more stable. In the interior part of the galaxy, that is within 40 kiloparsec, the data is more scattered, and the theory predictions are also widely different from each other. Then in the right, then in the upper right, we thought the same thing, but now in the log scale as a function of the observed expected Newtonian acceleration. And we find that for the interior part of the galaxy, that is the higher end of the acceleration, the expected profile of the are very, very different. And this basically means that this could be used to differentiate between theories better than any other acceleration relation. But we should also see that the data plotted in the Weyl here, they are also very scattered at this point. Now, meaning that the data could probably is not very accurate and precision in this particular in this particular part of the. And also we plot the mean average halo acceleration relation, which kind of shows a peak here, and then it increases again. So this is in contrary to what has been observed in the CNN co-paper in 2019. Halo acceleration data is always unimodal modal feature. However, if you look at MLS and the MOND profile, we do find that unimodal feature there. Weyl gravity, however, do not show a clear trend of peak in this particular case. So finally, we show the residuals in the lower panels here, and as one can find that the Weyl gravity residuals are better than the MOND and the MLS residuals. Finally, we plot the residual histogram here in this particular case, and which basically shows the same analysis that the Weyl gravity does a fairly better job than MOND, whereas the MLS is not being able to, that is the radar scaling is not being able to do as good as the other two models. Okay, so this study confirms a couple of things. The first one is that both the modified gravity theories in question, that is the MOND and the Weyl conformal gravity, as well as the radar scaling law provided by McGuy, can explain the radial acceleration data well. The data in the observed acceleration and the expected dynamic acceleration in the Newtonian plane is unable to discriminate between different models of gravity and scaling laws very well. However, if one goes to the halo acceleration relation plane, then the expected profiles in different theories of gravity are very different from each other, meaning that one should do a stronger test of gravity with the halo acceleration. Another important thing is that until now, in most of these studies, regime in galaxies to test different theories of gravity. However, this study confirms that both high acceleration regime and low acceleration regime are equally important for any test to discriminate modified gravity theories. However, as we have pointed out before, that the data in the inner core of the galaxy might not be very accurate. So as we obtained, so the current status of the data is not being able to discriminate the theories, but even though we understand that the theories can be discriminated in these particular region data. However, once we have better data, in the next couple of years, one can actually do a precision test for modified gravity using both high and low acceleration for galaxies, and of course, especially for the Milky Way. So with this, I'll stop here. See if there are any questions, and I'd be happy to address if I get any text or email. You can always. Thank you for your attention, and hope you have a good day.